Chapter 5 explains the process for calculating the strength of a structural joint that is either bolted or welded. Our discussion is limited to joints that are loaded in tension with no applied moments. If we want to join two pieces of structural steel in a building, we can either bolt them together or we can weld them together. Many welded structures are made by butting the two plates together before welding, but we are going to focus on overlapped welded joints only. Bolted joints have 4 different failure modes. We will look at each one individually, then we will analyze a bolted joint and calculate all 4 failure modes. Then we will calculate how efficient the joint is. The first failure mode of a bolted joint is bolt shear. This is where the bolt shears off because the applied shear stress is higher than the allowable shear stress for the material. P sub S is the shear force, and A sub B is the cross-sectional area of the bolt. The red line shows the shear plane for this bolt. Above this line, the bolt wants to move left, while below this line, the bolt wants to move right. What if there's more than one bolt? Let capital N equal the number of bolts. The more bolts you have, the greater the load the joint can carry. What if there's more than one shear plane? This bolt is carrying the load in 2 places, so we have twice the cross-sectional area supporting the load. Let lowercase n be the number of shear planes. The shear force is the product of 4 variables. There's a table in Appendix B that lists the allowable shear stress for 3 types of steel with 2 options about the threads. If the threads are in the shear plane, the bolt is typically not as strong because the threads act as stress concentrators. The load carrying capacity of the joint is the number of shear planes times the cross-sectional area of the bolt times the allowable shear stress of the bolt times the number of bolts. The second failure mode is called bearing failure. The bolt doesn't fail. Instead, the plate tears out. This is exactly how paper fails when you rip out a page from a spiral-bound notebook or a 3-ring binder. P sub P is the bearing force, D is the diameter of the bolt, T is the thickness of the thinner plate, sigma P allowable is the allowable bearing stress, and capital N is the number of bolts. You can find the allowable bearing stress for 2 different steels in Appendix B. The third failure mode is called gross tensile failure. This is where the plate fails some distance from the holes. This joint consists of 2 main plates that are butted together end to end and joined with splice plates. Either the main plate fails or the splice plates fail. In a lapped joint, gross tensile failure occurs in one or the other of the main plates. The load capacity of the joint is the cross-sectional area of the plate times its allowable stress. The fourth failure mode is called net tensile failure. Here, the plate fails at the bolt holes. In steel structures, we need a tolerance on the hole size so the bolts are easy to insert, even if the drill goes a little off-center when the hole is made. Calculate the hole diameter by adding 1/8 of an inch, or 3 millimeters, to the bolt diameter. The net cross-sectional area of the plate, A sub n, is the total cross-sectional area minus the holes. It's shown in yellow. The variable n sub f is the number of holes in the fracture plane. The easiest way to find n sub f is to draw an imaginary fracture through the holes. All you have to do is count the holes. The joint can support a load equal to the net cross-sectional area of the plate times the allowable stress. A lot of engineering design is done to improve efficiency. Lowercase Greek letter eta is used for efficiency. We can calculate an efficiency for the joint by dividing the lowest value of P sub s, P sub p, P sub g, and P sub n by P sub g. For example, if the results are 280, 500, 300, and 320 kips, then the lowest value is 280 kips, and the efficiency is 93%. If the joint efficiency is smaller than 100%, then the joint fails, not the plate some distance from the joint. If the joint efficiency is much, much smaller than 100%, then we are wasting material and the joint is under-designed. Maybe we can improve it by adding more bolts, or by using stronger bolts, or by using a thicker splice plate, or by using a stronger steel. Let's work out an example problem. Here's a pair of steel plates that are connected by a pair of splice plates. The main plates are 1.5 inches thick, and each splice plate is 7/8 of an inch thick. The plates are made of A36 steel, and they are joined by 8 1-inch diameter bolts made of A325 steel. The threads are included in the shear plane. The first thing to do is recognize that the problem is symmetric. Either the left half of the joint will fail first, or the right half will fail first. Either way, we only need to look at half the joint. Therefore, we're considering only 4 bolts. We can erase half of the diagram. Now we plug in values of all the variables, and the joint can support a load of 151 kips before the bolts shear off. For bearing failure, we need to figure out the value of T. The main plate is 1.5 inches thick. The sum of the splice plate thicknesses is 1 3/4 inches thick. Therefore, the main plate will fail first. Plug in the bolt diameter, plate thickness, allowable stress from Appendix B, and the number of bolts. The joint can support 522 kips before it suffers bearing failure. Next, we calculate the load the joint can carry before failing in gross tensile failure. It works out to 194 kips. For net tensile failure, we need to know the number of holes in the fracture plane and the hole diameter, which is 1/8 of an inch larger than the bolt diameter. The joint can support 153 kips before it suffers net tensile failure. Finally, we can calculate the joint efficiency. The smallest number is P sub s, so the joint will fail in bolt shear before it fails in any other mode. This is a good thing because bolts are cheaper and easier to replace than plates or beams. The last part of the chapter discusses lapped welded joints using electric arc fillet welds. Welding is an enormous topic, and we're going to touch only on one small aspect. You can read this section of the book for more detail, but what it boils down to is a simple equation for calculating the tensile strength of the welded joint. Multiply the unit strength of the weld by the length of the weld. Use the tables in Appendix B to figure out the unit strength, F sub weld. In this example, the total length of the weld is 10 inches. It's a half-inch weld using an E60 electrode. We multiply the unit strength by the length of the weld to obtain a weld strength of 63.6 kips. There is another table in Appendix B that you can use to figure out the size of the weld that's appropriate for the thickness of your plate. There are also 3 tips to good welded joint design concerning the length of the end return and the size of the lap. This section of the chapter doesn't cover stitch welds, butt welds, and other types of welded joints. It's designed to introduce the basics of strength calculations for one particular type of weld used in steel structures.